In this video we're going to have a look at the reactions of haloalkanes in the AS syllabus with aqueous hydroxide ions. Okay, so note it's aqueous. Ethanolic hydroxide ions are done on a separate video elsewhere. Ammonia and potassium cyanide. Alright, so this is also the mechanism for hydroxide ions is on the syllabus, which is done in one of the mechanism videos. So that will also give you some help in terms of working out products, etc. for this. Right, so we'll go through these, we'll look at the reactions, we'll look at the conditions that you need to be aware of, and we'll look at how to work out what the products would be. So again, it's functional group chemistry, guys. So what we're looking at here is whatever the functional group on the haloalkane is. Let's say it's just chlorine. That is where the chemistry happens. So if I have hydroxide ions, okay, what you'll notice about all three of these, actually I should have said, is that all of them have got lone pairs on them, and all of them are negative, or in the case of the nitrogen here, delta negative, and that allows them to react with haloalkanes because haloalkanes have a delta positive carbon here, and that is where the interaction takes place. That's why this reaction occurs, and if you look at the mechanism you'll see maybe a little bit more about that. Okay, so the lone pairs on the oxygen in this instance, the nitrogen in this instance, and the carbon in this instance will attack the delta positive carbon that's attached to the electronegative halogen in each particular instance. Okay, now so let's have a look at first of all this one, and very simply, just like any of our functional group chemistry, all we do is we take one out. Okay, in this case the Cl minus is gone, this bond has broken in here. Okay, heterolytically meaning that we end up with a positive and a negative ion, so both electrons in this bond have gone to the chlorine, and we get the OH, which forms a new dative bond. If both these electrons have gone, the new bond is formed by the lone pair on the OH, and we get an alcohol. So we've gone from 1-chloropropane to propan 1-ol over here. Okay, that's as simple as it is. This reaction occurs in aqueous solution, okay, and it is carried out in heat under reflux. If I wanted to get my final product out at the end in some form of purity, I would distill that product. Okay, we'll look at another one. We'll just look at one here where maybe we have two groups, but really all we do, guys, is exactly the same again, but we will need two. On the examiner we need two OHs, and the examiner will probably tell you here you've got excess potassium hydroxide or sodium hydroxide, whatever the source of hydroxide ions happen to be. And once again, all you do is you replace the bromines in this instance with OHs, and you would of course get, in this case you will end up with propan. And don't forget the E when you've got two OH groups, and it's number 1 and number 3 hyphen diol. So up here we just had propan 1-ol. Now we've got propane diol. We need to put that E in. So conditions and everything are exactly the same. Okay, pretty straightforward, I think, that, hopefully. Right, let's have a look at the reaction of the ammonia then. So we make a whole new functional group that you haven't met before. The last one we had met alcohols in G. So we'll have a look at the reaction of the haloalkanes with ammonia. Again, this is another nucleophilic substitution reaction. If you think about your ammonia, it acts as a nucleophile again. It's got the delta negative nitrogen in here because it's more electronegative than the surrounding hydrogens, and it's an asymmetric molecule. And we've also got a lone pair on the nitrogen, which is capable of donating those to the delta positive in this region, this carbon region of the haloalkane molecule. So we'll look just at the conditions next. So the solvent we use this time is ethanol, unlike the aqueous potassium hydroxide where we wanted lots of hydroxide ions in there. Two reasons for using this. First of all, haloalkane is not particularly soluble in water. So when we did use aqueous potassium hydroxide in the last one, you'll probably use a mix of ethanol and water. as your solvent, although it's frequently just referred to as aqueous. We don't want water in this as a solvent because we want to avoid hydrolysis. And if you think about water, water does contain, even though whether you know it or not, it does contain a certain number of hydroxide ions, and that would lead to the formation of an alcohol, just like the reaction with potassium hydroxide. We want to avoid that. The next thing is we can't use heat in our reflux this time because we use instead a sealed tube, and that avoids ammonia being lost in reflux. So ammonia is a very volatile, low boiling point gas, and when you warm it down here in the reflux condenser, all it will simply do is rise up and go out the condenser and get lost. So we do this reaction in a rather new condition for AS chemistry, and that it's done in a sealed environment. And we also have to heat it, and that's just again like reflux, to break the bonds, the strong covalent bonds, and overcome the high activation energy. So we'll look at a few of the reactions in the equations and how to name the products made here. We make a whole new functional group here. Okay, so we look at the reaction just with ammonia, and just highlighting here really in the blue the sort of the region of the delta positive carbon that the ammonia can attack. And it does attack that in a nucleophilic substitution reaction, and we get the Cl removed and it's replaced. Now we need to be a little bit careful because in the previous reactions we've just removed one thing and replaced it with another, but this time the NH3 is turned into an NH2. The nitrogen here can only accommodate 3 bonds, as you know, but if we just sub the NH3 in, we would end up with 4 bonds of the nitrogen. So that's a common place for mistakes to be made by students. So please just be careful from that perspective. Okay, and that we have we are only able to accommodate 3 bonds here, and it has to be an NH2. Okay, now the compound that's made there is 3 carbons long, and it has this new functional group. So it is now an amine, and it's called propan-1 amine. Propan-1 because we could also have the amine group there, that would be making a propan-2 amine. So just be cautious from that perspective. Okay, and you get your side product of hydrogen chloride. It would be, we start off with a chloroalkane there. Next then, and just all I've done here really is I've put the bromine on a position number 2 just to show you what would happen if that was the case. And again, we just remove the halogen and we put the NH2, not NH3 here, and again we account for HBr. This time we have 4 carbons in the chain, so it's a butane, and it's on position number 1. 2 is our lowest number, it's a butane-2 amine. The last one we want to look at here then, I've just looked at here where we've got a di-haloalkane reacting with ammonia, so we need 2 ammonias this time, and the exam will probably say something like there's excess ammonia, so therefore you can substitute all of the halo groups, and we get the new product where we just take off the Cls like we did above, and we replace them with NH2 groups. Okay, we will need 2 HCls this time, okay, just to account for the loss of the 2 chlorines. And now just be careful with the name on this occasion because we will get butane-1,3 diamine, but we've got to put the E here this time to illustrate that we've got 2 functional groups, diamine in this case. Okay, so hopefully that covers most bases with regards to the reaction of ammonia with the haloalkane, and you can tackle a few of those in your questions or past papers you need to be aware of in order for this reaction to occur. We'll look at the reaction now of cyanide ions. Okay, so cyanide is highly toxic, so you wouldn't be doing this in a lab. So this with potassium cyanide, but it's the cyanide ion within that which acts as the nucleophile. Alright, so we start here with 1 chloropropane, and again simply we remove the functional group and we get, there's a triple bond between the carbon and the nitrogen, by the way, okay, which you would need to be aware of. Sometimes they ask you to draw that out. Now the key thing we need to be careful of here is that we now have added another carbon to the chain. So instead of having a propane now, we have 4 carbons, and these are just simply called butane nitrile. Okay, let's have a look at another one. Let's take Br here, so 2 bromobutane, okay, with our cyanide ions. Okay, I should have accounted for Cl minus there as well, sorry. So we just take off the bromine, put our Cn on, okay, and then we have our Br minus here. If you did decide to use the full equation and write potassium cyanide, by the way guys, the K there, it would just be your byproduct of KCl and KBr, okay, without the charges on it. Obviously those negative charges would disappear at this instance. Right, again we've added an extra carbon into the chain here. Now this is my functional group, so that needs to be part of the main chain. So instead of my main chain being in that direction, it's now in that direction. So this group here now becomes a methyl group. So I have 2 methyl butane nitrile. So be careful of that. I should have a wee hyphen in there. Be careful of that. That catches some people out where they try and call this something like 2 butane nitrile or butane 2 nitrile, thinking that this is my overriding longest carbon chain here. But no, we've got to incorporate our functional group into that, so just don't let them catch you out there. I'll just look at one other little thing here, the dot cross diagram of a cyanide ion, which they frequently would ask you. The conditions for this, by the way, are heat under reflux with the potassium cyanide dissolved again as in ethanol. The reason why we use ethanol, by the way, also as a solvent is because if we use water, you may not know this at lower six, but water actually contains some hydroxide ions. So therefore, if we did use water as a solvent, we would tend to get a lot of some alcohol produced. So for these reactions, we avoid using water because we don't want hydroxide ions in there. Okay, if we use ethanol as our solvent, we do have an OH in there, but that is not a hydroxide ion. That is a covalently bonded OH, okay, hydroxyl group, which is a different thing altogether. Okay, right, I'm just going to do the dot cross diagram of a cyanide ion, which they frequently ask. So this has come from potassium cyanide, which is ionic, so that's the charges, which means the potassium has lost an electron. So if we draw this, we have a triple bond here. Now the nitrogen had 5 electrons to begin with, so it's got 3 left over. Okay, the carbon had 4 electrons to begin with, so it's 1 left over here, and people then struggle to find where the 8th electron comes from to give. So the nitrogen's fine, it has a full outer shell. But remember, the potassium, has lost an electron. So the other electron is the one that has been lost by the potassium in this instance. Okay, and it's good practice to show that in a different way. Okay, so to show it, I've shown it just as a little square here, and that's as good a way. The other thing when you're doing this and you finish that off, it should really be put in square brackets and a negative charge shown distributed over the entirety of the molecule. Okay guys, I hope that helps you understand how to write equations for these reactions, how to name the products for these reactions, and finally how to understand the conditions and just really quote the conditions that are used, and maybe also explained a little bit to you why we use some conditions in these particular instances. Okay.